University of Padua back in 2018. Just spent about 3.5 years, give or take, both in the US, first at the Slovenian University in Africa, and then about a year, less than a year, at the University of Vienna. And she's presently, since spring 2022, one of the CM fellow the Instituto of the Canarias. She's an expert in exoplanet detection techniques, both on the ground and space. And today, she will tell us a little bit of knowledge that we can gain by combining radio velocity and transit work. Please.
Well, thank you, Alessandro, for the introduction. So today, I will talk about the young exoplanets and specifically about GAPS and the program that we are carrying out within GAPS to study this young exoplanet population. Well, this is just an outline of my talk, and I will introduce some background, some scientific background. So what we know about exoplanets so far, and some hint of planetary formation and evolution. And then I will talk about young stars, so giant planets around young stars, why these are important to study. And since young stars are also active, we need to deal with the stellar activity. So I will just show some methods to deal with the stellar activity when we study young exoplanets. And then I will present you the Young Object Program from GAPS. And so the survey and the observational strategy that we need to deal with the stellar activity, and then some results from this program. So the first clues of a global picture that we are trying to understand. So since Alessandro introduced me, I will introduce GAPS, even if probably most of you already know about GAPS, but to be complete, GAPS means Global Architecture of Planetary Systems, and it's an Italian collaboration with scientists working in the exoplanets field. And since 2012, we are carrying the long-term observing programs with the spectrographs at TNG, so HARPS Nord and JANO, and also through the JARPS mode for some specific science cases. And the main objectives are the characterization of these planetary systems, and also the understanding of the origin of the diversity that Kepler and Tess discovered about planetary systems. So very briefly, because most of you know this, but one of the main questions that we want to answer within GAPS is why these exoplanets are so diverse, these systems are so diverse. In fact, before the discovery of the first exoplanet, our solar system was the only example of the planetary system. So the only theory conceived and developed in that case was based on our solar system. So inner planets are rocky, outer planets are gaseous. But with the first exoplanet, this theory was completely challenged because the first exoplanet discovered was a hot Jupiter, very close to its host star. So this challenged our understanding on how planets form and evolve. Since then, we did an enormous progress in the exoplanets field with Kepler first, since 2009, where we discovered a lot of different planetary systems. So we understood that the solar system was only one option among like a wide range of possibilities of exoplanetary systems. And then with TESS now, since 2018, and I like this picture because there is Kepler passing the torch of exoplanets to TESS. So like Kepler, with Kepler and TESS now we know more than 5,000 confirmed exoplanets. And many of those, like super Earths and hot Jupiters, are not present in our solar system. So why these exoplanets are so diverse from like our solar system? So far, there isn't a unique theory to explain all these different observed features. And for close-in giant planets, there are few theories, like the smooth disk migration, where the planet, so probably I can mention three theories. One is the in situ formation, where the planet, can I point here? You, but I don't know online, but okay. Where the planet is forms where we already observe it, or there is the disk migration where the planet form far from its host star and then it migrates through the disk, and then the disk disappears and we see the planet where we observe it in the present. And then there is the high eccentricity tidal migration, where the planet again forms far from its host star, but then it interacts with other planets or with a distant stellar companion, and it is pumped into an eccentric orbit, and then there is the tidal dissipation, which circularizes the planet's orbit. We expect to observe different characteristics depending on the type of migration. So, for example, here I just put some of the observable that we can study. Like for the disk migration, we expect small eccentricities and spin-orbit alignments, while for high eccentricity migration, we expect for longer period eccentric orbits, or also spin-orbit misalignment. And for, depending on the migration, we also have different time scales. So for the smooth disk migration, this migration happens within the first 10 million years, more or less, while the high eccentricity tidal migration within 1 giga-year. The observed planetary properties like the orbital architecture, the internal structure, the atmospheric composition are the result of a very complex mix of physical and dynamical processes, and these processes happen at different time scales. So the planet formation depends on the properties of the disk, depends on whether the star is a single star or a binary, and whether the system is forming in a crowded environment or in an isolated environment. And then the orbital evolution depends on the type of migration, and if the orbital depends on the orbital inclination and also on the tidal dissipation that can happen. And then the radius evolution depends on why the radius and how the radius is evolving, so by contraction or by photoevaporation or by core-powered mass loss. These are just few characteristics that we can study while observing this planetary system, and these are all different mechanisms and processes that mostly happen during the first hundreds of million years. And so all these processes within the first hundreds of million years shape the planetary system that we see right now. So this is why it's important to study young exoplanets. So exoplanets within few hundreds of million years. Young planets are important because we are looking at the architecture of these systems during their infancy, basically. And also young planets are unique because we can investigate both the inner and the outer region of the system through different techniques. So the inner regions can be investigated by the radial velocities and the transit technique, and the outer region by the imaging technique. And in particular, close-in planets are easier to study and to follow up because they have shorter orbital periods, and so they are very easy to follow up and characterize with radial velocities and transits. So an important question that we want to answer within GAPS is also how frequent these close-in giant planets are around these very young stars. In fact, a work by Donati et al. 2016 showed that these planets might be more frequent around younger stars than major low-mass stars. So they suggest a high frequency of hot Jupiters around young stars. And this is one of the questions we want to answer within GAPS Young Object Program. But a great limitation in the observations of young stars is the stellar activity. So young stars are also active stars, and the active regions alter the profile of the spectral lines, which is seen as a spurious radial velocity variation. So there is an intrinsic radial velocity scatter, and the fast rotation of the star can blend the line, so we can lose the Doppler information. So basically, the stellar activity can either hide, hamper, or mimic a planetary signal. So young stars, young planets are difficult to detect with a blind search with radial velocity technique because the stellar activity hamper the Keplerian signal. And this is why the current statistic is far from being completed and suffers a lot also for detection that are not confirmed by other independent techniques. So there are several claims around young stars or planets around young stars, but also there is a quite large rate of retractions of these planets. And I will show you some of these results within GAPS. So as I told you, we need to deal with the stellar activity when we observe young stars with the radial velocities, and there are different techniques, different methods to do this. I here go I will be short in showing few of these methods. One of these is the bisector analysis. The bisector can measure the asymmetry of the spectral lines, and so this allows to understand the variability of the line profile, so the stellar activity. And we also have spectroscopic activity indicators, so there are spectroscopic lines like the calcium, H and K lines, the H alpha, the helium. So at different wavelengths we can have different activity indicators, and we can investigate the correlation between the radial velocities and these and the bisector, or the radial velocities and the activity indicators lines. If there is a correlation, it means that the radial velocities are affected by the stellar activity. Another powerful tool to deal with the stellar activity is the Gaussian process regression. This is a tool to mitigate, in general, to mitigate a correlated noise. So in our case, we can mitigate the stellar noise. And this is a non-parametric method, which means that we don't need to know the shape of the stellar activity, of the activity signal. On the other hand, this is an intensive, computational intensive method, and we need a large data set to be fine with this method. Also, another very effective method to deal with the stellar activity that within GAPS we used it for few cases is the multi-wavelength high-resolution spectroscopy. So we can couple visible and near-infrared data And this will allow us to disentangle the activity signal from the Keplerian signal, because while the activity is chromatic, so it changes the amplitude of the radial velocities, changes through the wavelength, the Keplerian signal should not change through the wavelength. So one emblematic example is the TW Hydre, where Setyawan et al. 2008 with Ferros data, which are which is a visible spectrograph, claimed a 10 Jupiter mass planet, and the same year, Wellamo et al. With only 5 Crires points, they actually retracted this planet, because the near-infrared points were basically flat with respect to the visible one. And this is a star, a T Tauri star with 10 million years old, and it's very young and very active. So this showed the power of this technique. So this multi-wavelength multi-wavelength observation technique was evaluated by GAPS, and within GAPS we decided to develop the GAPS project, which aims to couple JANO and ARPS, so near-infrared and visible spectrographs, in order to have simultaneously high-resolution spectroscopy. So this means that 2 spectrographs can work simultaneously, pointing the same target. And this was led completely by GAPS, so by INAF and within GAPS, and was this kind of observing mode is offered at TNG now since April 2017. And I will show you some results with the JARPS observations. So a step back, so I said that the radial velocities can be very affected by the stellar activity, so a blind radial velocity search is difficult. And it is easier to first look at the transit candidates and then follow them up with the radial velocities. And this is because the planet detection with photometry is less sensitive to the stellar activity. In fact, you can see from this plot that if the stellar photometric modulation is not extremely variable, the typical transit duration which is a few hours, is shorter than the rotational modulation, which is a few days. And so uninterrupted photometric time series are in principle less affected by the stellar activity with respect to the spectroscopic ones. So TESS is providing us robust candidates to confirm and characterize with the radial velocity technique, and GAPS at some point decided to apply this, to go to this path. So not blind search anymore, but full radial velocity follow-up of transiting candidates. So this is like a slide to present the Young Object program. This is one of the programs that we carry within GAPS. And this project is currently performing this investigation, so to study young planets. And we are monitoring very young, so less than 20 million years, and intermediate age, younger than few hundreds of million years stars, to search for Jupiters and study the first stages of the planetary formation and evolution. And then also we want to confirm or not the high frequency of Jupiters around very young stars. And we are applying an observing strategy, which is like collecting a lot of epochs, I would say at least 50, but we are more on 100 for each target in order to overcome the stellar activity, but we are also using sophisticated methods for the analysis, such as the Gaussian processes that I talked about earlier. And here I also want to stress that this program is carried out by people who are among almost all the institutes, enough institutes. And also, since I am here in Turin, I can advertise this institute. So also here in Turin, with Mario Damaso, Matteo Pinamonti, there is a big amount of work here within GAPS Young Object. So I will present finally some results from GAPS-Yo. This is the case of BD plus 2017-90. First of all, as I said, like since young stars are active, when we see a signal, we need to wonder, is this a planet or is this a stellar activity? So this star, this planet was claimed by Hernan Obispo in 2010, and this is with ARCS North data. And then the same year, Figueira published this result with Coralie data, which is always a visible spectrograph, which were almost completely flat with respect to Hernan Obispo data. And then 5 years later, Hernan Obispo decided to collect all the archival ARCS North data, and he reclaimed this planet again with this. But as I said, like all this debate was based on visible data. And within GAPS, we decided to follow this target also with Giano, and we follow this target during the JARPS commissioning, and these are the results. So you can focus on this plot where the dashed line is the model from Hernan Obispo 2015, and our data, so Giano data and IGRINS, which is another American near-infrared spectrograph, are here, which are completely flat. So we could actually confirm that this is not a planet, at least not that planet. And also here you can see what I was talking about before, a correlation between the radial velocities and the bisector, which indicates that the radial velocities in the visible field, so these are ARCS North radial velocities, are very affected by the stellar activity. Okay, so we killed this planet. So the answer is this is stellar activity. Another story. We have the AD Leo case where Tuomi et al. 2018 claimed a planet with a not Jupiter with IRIS and ARCS data. And well, here I would like to note that, to stress that the rotational period is very close to the orbital period. But yeah, they did some tests like splitting the ARCS and IRIS spectra in different wavelength chunk or in different seasons. So these tests were passed. So they just claimed this planet. And we performed JARPS observations. And these are only the ARCS North data. And here you can already see that with different methods for extracting radial velocities, we have slightly different semi-amplitudes. So this is already a hint of something that it's going on here. And these are Giano data. So, I mean, they are very scattered and they don't follow at all the visible radial velocities. So also in this case, we killed another planet. We kept monitoring this star with GAPS Nord and for another season, and this is the result. So only also with GAPS Nord, you can see that the semi-amplitude for the second season dropped from 33 meters per second to 13 meters per second. So what we learned here is that we can save a lot of telescope time if we do multivariate observations, because with the near infrared, you can have the comparison immediately instead of keep monitoring for years or months, I don't know, a star, waiting for the activity to change, or probably it will never change, I don't know. But yeah, we learned this lesson. And after killing 2 planets, we finally confirmed one. And in fact here, well, simply you can see that the Jano radial velocities match completely with GAPS Nord and other like, trace radial velocities. So we finally confirmed one. And another case is V1298 Tau B, where this is a very young star. This is 2 million years. And Donati et al. 2016 claimed a 5-day planet with the espadons and Grace's data. And we observed this star within GAPS for a long time. This is a 3 seasons observations, and this is a work by Mario Damaso. But the radial velocities here are very dominated by the rotation. In fact, like the radial velocities that you see here are phased to the rotational periods. And with 3 different radial velocity extractions and different models, we could not recover this hot Jupiter. Another intriguing system which GAPS invested a lot of time with is V1298 Tau. This is a 4 transiting planets discovered by K2, a 20 million year star, and we observed it with GAPS Nord, but then we also joined the Spanish team. So they observed it with Carmenes, and with this joint effort, we collected in total like hundreds of radial velocities. And with these hundreds of radial velocities, we could determine the masses of the 2 outer planets. Here in the table, you can see B and E. This is a strange name because, well, so these are the outer planets, and we modeled the activity with the Gaussian processes again, and this mass determination indicated an high density for both planets. And this is a work by Suarez Mascarenhas and Mario Damaso, and within GAPS we also have a group of people working on simulations of photoevaporation simulations, so atmospheric simulations, and we performed this simulation for these 2 outer planets, and there is no evaporation expected for both planets, which means that within 20 million years of age of this system, these planets already have lost all their atmosphere. So this can give some constraints in the time scale of the photoevaporation. So again, we kept studying this system to understand the link between the densities, the high densities of these planets and their history, their migration history. And there is a work by Diego Turmini who performed N-body simulations on this. And the main results, so as you can see from the plot, the main result is that, so these points are the current position of the two planets, while these 2 points are the initial position. So they demonstrated that these planets formed at least 3 times farther, so more distant than the current position. And the current architecture for this planet presents no resonant chains, and it's an unstable system. So according to this work, the most plausible scenario for this instability, to explain this instability, is a planet-planet scattering scenario. But, like I would say, but Sphere and Gaia data exclude additional massive planets. So these are the main results from this work. And another star is TOI 942, that I would say it's the most boring among all stars and systems that I'm presenting today. But at the time of the publication, this was the youngest multi-planet system discovered by TESS. Now it has been dethroned by AUMIC, so it's not even the youngest one, so it's the most boring. But we observed this target only for 1 season with ARCS Nord, and in fact, from the periodogram, you can see that we can see the rotational period, but we cannot see the other 2 signals from the planets. So we could only validate this system, and we could only put upper limits in the masses. But we are keeping monitoring this target in order to determine the masses of these planets, and also this is being followed up by Cheops for TTBs in order to search for additional companions. So, as I said, within the GAPS2, we also have the team to simulate photo evaporation, atmospheric photo evaporation. And for planet B, we can see that a quick photo evaporation within 100 million years is expected, while planet C can lose its atmosphere over longer timescales. But of course, this is based on upper limits of the mass, so it's not a conclusive photo evaporation model. But after the youngest multi-planet system, we also discovered the youngest ultra-short period planet. So this is TOI 1807, published by Domenico Nardiello last year. And here we could actually recover the mass through our ARCS Nord radial velocities. So now this planet belongs to the small sample of ultra-short period planets with masses and radii measurements more precise than 30%. So here are these USP that I mentioned, and here is TOI 1807b. So this planet it's consistent with a rocky terrestrial composition, and probably with an iron core between 25 and 50% of the total mass, which is in line with a large part of the USP planets here that follows the Earth-like composition line. Now, on the basis of these planet parameters, we exclude the presence of an extended envelope, an extended atmosphere, which means again that, so this was a 300 million year star, so within this time scale, this ultra-short-lived planet already lost all its atmosphere. And here, to the right, you can see another plot with black points are the confirmed and candidate exoplanets in crowded environments, so in stellar clusters, association, and the gray points, the gray squares, are USP planets. And here we can kind of split this plot in two regions. The planets with like smaller planets, so smaller than 4 Earth radii, and larger than about 4 Earth radii. And here we can see that the smaller planets are all like in the old region of the stars, and the bigger planets are in the young age region. Now, in the first case, it can be very probably an observing bias, because it's difficult. It's more difficult to discover very small planets around younger stars, while in this region, I don't know if we can claim for a observing bias, because it should be easier to observe big planets, basically around orbiting older stars. But from here we can see, I mean, there is a hint of a radius evolution. So young stars, young exoplanets seems to be bigger, to have a bigger radius, and then while they age, they shrink their radius. Of course, like for young stars, we have a lot of biases for the stellar activity, so these remain a hint suggesting for. Okay. So this is one of the most recent results from Mario Damaso, of course, for GAPS Young Object Program, TI 7026. Here we could actually recover only the mass of the outer planets and not the inner, but there is again a collaboration with the Spanish team. So we are putting together all our data sets in order to have a mass determination also for the inner planets, for the inner planet. And here, in this case, different models give different results. So you can see from this plot, these 2 points are the same planet, but with different models. And also, so this is the outer planet with the mass determination. And these 2 are the inner planet upper limits. So in this case, like the stellar activity is very difficult also to model with different approaches. But again, joining the effort with other teams is leading to a more precise mass determination in this case. This is not yet published. Probably the paper is drafted, but I don't know much more than this. But now again, we perform the photoevaporation models. The modeling also for this planet, and it seems that these 2 planets have different time scales for the photoevaporation. The planet B will lose its atmosphere within 100 million years, so it's already lost its atmosphere since the age of the star is 400 million years. while planet C has very long time scales for the photoevaporation. And in fact, this is demonstrated by the work by Zhang et al. 2022, because they observed this with HST and Lyman alpha, and this is the Lyman alpha absorption excess for planet C, which means that planet C has an extended atmosphere, so an ongoing photoevaporation. And another result, which is, I'm working on this target, but this star is more than 1 gigayear old, is this TOI 4515. Well, this is a work ongoing work, so we don't have much to say, but here I want to stress the eccentricity of this system, which is very high and very clear from the data. And this is a kind of an old star, so we need to try to put these two information in the context. But so far this is a preliminary analysis, so we are working on this. Now, I don't remember. No, I don't remember now. Then we have, well, this is not strictly part of GAPS young object, and I will go very fast on this, but within the GAPS young object group, we also had some programs, like satellite programs, to observe, for example, the DS2A and TOI 179 with ARCs, so from the south. And so we also have these results from other satellite programs, which are related to the young exoplanets, not strictly related to the program. But for example, here I would like just to show you that here we have the radial velocity. So I said before, with the hot Jupiters around young stars, we can actually study the inner regions with the radial velocities and transit, and the outer regions with the imaging. And this is an emblematic example of this, because we have the radial velocities showing a Neptune mass planet, and then we have sphere data, which shows a low mass companion in this system. So, and in the radial velocities, we can actually see a trend, a long-term trend due to this mass companion. So we can actually characterize these systems very well with almost all the techniques, exoplanets techniques. Okay, this is my last slide, which is putting together all these results that I showed you. And I would like to put your attention in this plot. These are all the currently known planets, and young planets are overplotted with colors, and these are younger than 1 gigayear. And we can see few things from this plot. So, like the ones with the circle, with the black line circle, are the ones from the GAPS Young Object Program. So, one first thing from this plot is that our program is giving a significant contribution to the young sample. And the scientific result from this plot is that most of the youngest exoplanets, so younger than about 100 million years, are in a region which is not so populated. And it's like the black arrows, for example, here are 3 planets where within GAPS-EO we simulated the photoevaporation. So where the end of the arrow is the final position in radius for these 3 planets. So this means that we are expecting that young planets are moving down in this diagram. So again, this is a radius evolution hint of these young exoplanets. But again, we have a selection bias because we need to deal with the stellar activity. And we discovered only few young planets due to the difficulties related to the stellar activity. So observing biases may be present, but these first results show at least a possible radius evolution with time. And I'm done. I leave you here with the conclusion and happy to have questions.
Thanks a lot for this very comprehensive list of very interesting results. So, we can open the questions, both online and
First, hypothetical questions. If you have all the time in the world,
Yes.
how big is how sample limited are you? How many good capture properties you have?
So, hypothetically, if we have all the time in the world, so first of all, we should observe much more than now. Like the sample that we have, we should observe a lot to overcome the stellar activity. So this will be much easier to recover the Keplerian signal. And then your question is, which could be the sample? Like how many planets we can? So, well, yeah, probably so I'm going back here. These are all the planets that are younger than 1 gigayear, so that we can consider young planets. And they are it's a very small sample with respect to the 5,000. But again, this is a bias, and we are now taking targets from tests. So I don't know the answer. I don't know the number of how many young planets we can observe. But if tests keeps giving us targets, probably with tests probably double this. But without tests, with a blind search, it will be very difficult. No.
Yes, anyone. So if you compare the slide with the outer planet discovered in the imaging.
Okay.
Next one. So you remember the symmetric axis of the outer planet. So we show that the linear planet that we see in the residual.
This is not a planet. This is a star, like a stellar companion.
It's a low mass. So, okay.
But it's a star.
Okay. And so are we sure that the planet we see in the RVs this low mass companion?
Sure. So sure, probably not. But these. So at the beginning, they. Nancy, don't know if it's present, you can answer. But at the beginning, this was thought to be due to the stellar activity, and this is why they tried with GP and without GP, and the trend is still there. So they could rule out the fact that it was due to the stellar activity, but
so it's unclear if it is due to the low mass companion or the additional bodies.
Yeah, they suggest this can be due to the stellar companion, but Is that the one? Just to be clear.
Okay, any questions from the audience? I have a question. The filmmaking is that the object that you are working on, on the very high centricity.
Well, most of the answer is I don't know because we didn't. Yes, but
It's interesting to know that the station of the field here
yes,
is identical. I don't say.
yes. So we applied a lot of models, and like with GP, without GP, and it gives almost the same result. So it seems that the GP is able to deal with the stellar activity at 15 days. It is true that so the distributions are very sharp. It is also true, and I mean also when I was trying models with an orbit, with a rotational period larger than like with a range between 7 and 20, it could still recover the rotational and the orbital periods. So
Possibly this is the case which we disentangle entirely the two contributions because of the very different amplitudes. How do you remember how large is the signal?
it's not so large. It's like 20 meters per second, and the planet is 300. So yes, this is probably an easy case, even if the periods are very close.
Because we historically struggled with number of systems which having better signal flows to some of them. When the amplitudes are comparable.
Yes.
Signals. So, any other question? Okay, if there is no one really commenting from the audience, I think then we can thank a lot Ilaria again.
Yeah, thank you.
Okay.
Ciao.
Bye-bye.